Today will be about explicit construction of the spherical harmonics. So we consider again the orbital angular momentum, and we look for two states. Okay, in the previous notation we would use say J and M. Here I will use the fact that this is a function, so it's rather than J I will use L, M will be still M. Okay? So these are functions of theta and phi, remember? And the only possible values of L square or J square are L times L plus 1, okay, times the same function. Okay? Sometimes I will write phi like this, sometimes like this, okay? That not corrected. In fact, in LaTeX you have both, okay? So you can choose, okay? So, I mean, it's unfortunately random. 1/2 of the time it comes wrong. Okay, so these spherical harmonics are eigenfunction also of Lz with eigenvalue m. Good. Now, I remind you that these are differential operators. This operator here is very simple. I'll give it to you. It is minus I, the derivative with respect to phi. Okay? You see phi is wrong. Okay. This is orderable. Okay? I don't even write it. If you want, I can write it. Okay? Well, just to give you an idea of what I mean orderable. Okay. I write it up here because I will never really invoke it. It's minus the second derivative with respect to theta 2 times plus 1 over the tangent theta, the first derivative, plus 1 over sine squared of theta, the second derivative with respect to phi. Okay? So, we will see that this differential equation is easy to solve. But if you ask me, please solve that, I would refuse myself. Okay? Be just advice. I would never, adventure in trying to solve that differential equation. Okay. Let's start from this. So this differential equation, I write it explicitly, means that the derivative with respect to phi of this function of theta and phi is equal to, you see, this is just unavoidable, is equal to m times the same function. Okay? How do you solve this? Let's argue together. So you take a derivative, minus I the derivative equal to some number. Remember, this is like an eigenfunction of this momentum. It's not a momentum, but looks like minus I the derivative with respect to x. So you know how to solve it. Right? It's a plane wave. So the result is that y of L, m, theta, and phi must be equal to e to the I, m times phi, okay? Times what? Times the function of theta, right? Theta plays no role, but still appears there. Any function you can do it. Obviously, this object here, in principle, depends on L and M, right? But that is otherwise general. Is it clear? If you take a function of this form, you take a derivative with respect to phi, okay? Automatically, you get this. Obviously, this is factorized. Okay? Good. Now I ask you, this is a function in space. Theta and phi are the latitude and longitude. I want a function that is a unique function. So if I have a point, I want the value of the function at that point. Notice, I don't simply want that the modulo square of this is well defined at the point. I want the function at the point. Okay? Now you realize that if I have on the sphere, okay, so this is, say, theta, and this is phi, okay, the angle phi. Now, if I have a phi, and I change phi into phi plus 2 pi, I get to the same point, right? It's the same point. However, if you change in this function e to the im phi plus 2 pi, I pretend that this should be the same thing as e to the im phi. Okay? Otherwise, it makes no sense to write this as a wave function in space. When this happened, what m do you need to have? Sorry, is it okay? Is it clear? This can be erased, right? So I want e to the I 2 pi times m equal to 1, right? But if m is half integer, this is minus 1. So m should be integer. Okay? It's a very nice conclusion. So for orbital angular momentum, the quantum numbers m are integer. Otherwise the function is not defined, which means that L is also integer. Okay? So half integer is not good for orbital angular momentum. Alright? Good. This is the first interesting conclusion. Now we proceed. Remember that this is a tower of states. Okay? In particular, two L plus 1 states. Remember the construction. Okay? So if you fix L, I do have the state L, L minus 1, all down to L minus L. Okay? This object here is the number m. Okay? So the maximum m is equal to L minus 1 up to minus L, and you have two L plus 1 states. Okay? Let's start constructing this. Okay? In other words, I want to construct, this is the Keck notation, but I want to construct y L of theta and phi. Okay? The top state. Why is the top state simple? It is simple because you know that if I apply L plus to the top state, what do I get? I get 0. Okay? This is annihilated if I try to apply L plus. Now, L plus is more complicated than LZ, but still manageable. Okay? I'll tell you what L plus is. Okay. L plus is Lx, so this is equal to Lx plus I Ly. You can calculate from the differential expressions we have is I e to the I phi minus I, the derivative with respect to theta, plus, well, it's 1 over the tangent of theta, the derivative with respect to phi. Okay? This is L plus. Very good. Now I ask you, let's try to insist that this object is equal to 0. So I rewrite this expression explicitly. I want, since I know that this object here is equal to P, oops, unfortunately not a good, no, I have to use this. P L of theta e to the I L phi, okay? I'm using the fact that I know that for L here there is an L, okay? And then I have this expression here that I have to apply to this operator, okay? Shall we do it? Okay. So this is equal to I e to the I phi, comes from here. Then I have minus I, the derivative with respect to theta is applied only to the PLL. Okay? I omit the variable. And then I have to multiply still by e to the I L phi, which is this. And then I have plus this, plus 1 over the tangent, which is the cos theta over the sine theta. The derivative this time applies to the phi term. Okay, so I have the PLL of theta times the derivative, which brings down IL, and then you get this. So, okay? Is it clear? So this is the algebra you need to do. Now you see that this factor here can be in fact put in common. You can put it outside, and the remaining object is I e to the I L plus 1 times phi. And then the term that you have there, oh, by the way, there is an I, which you can take out also. So let's put this I put it I squared. And then I have minus the derivative with respect to theta of PLL, plus I have here L, then I have the cos theta divided by the sine theta, the P spherical, PLL, okay, this should be equal to 0. But how can something which is minus something different from 0 times this factor here be equal to 0? You deduce that the derivative with respect to theta of PLL of theta is equal to L, the cos theta divided by sine theta times PLL of theta, right? If this is satisfied, this is 0. Good. What is a function whose derivative is this funny object here? Now, it's not a differential equation that they encounter every day, but still, I mean, it can be solved, okay, in many ways. But in particular, I will just give you a guess, okay? The guess is the following. If I have PLL of theta, suppose that I have some constant times the sine of theta to the power L, okay? I suggest you the form. If I take a derivative with respect to theta, you bring down L, and this becomes L sine theta to the power L minus 1. And then I have to take a derivative of the sine, which gives me the cosine. Okay? But you see that this you can write at e to the L divided by the sine theta. Okay? So precisely the factor that you get by taking the derivative are L, a cosine, and divided by the sine. You see? So, needless to say, this is the solution of this. Obviously, you have to normalize appropriately with the coefficient CL, but this is just, you go and you look for tables so that these objects are appropriately normalized. So the normalization that you require is that the integral over the theta from 0 to pi, the integral over the phi from 0 to 2 pi of the modulus square of Ln of theta and phi is equal to 1. Okay? And since the modulus square of this object is 1, is essentially the modulus square of this p that you have to integrate over theta. It's an integral. You do it, okay? And if you do it, you will realize that this CL has to be, okay, I write it here. So let me erase part of this algebra. CL has to be equal to the square root of 2L plus 1 times 2L factorial divided by 4 pi, and then there is an extra factor 2 to the L factorial, okay? Now, in principle here you could put 1, but the convention is that you put minus 1 to the L. So depending on L being even or odd, you put plus or minus 1. Okay, this is just a convention, because after all, what you really require is the modulo squared. So you could put any phase, but this is the standard convention. Okay, good. There we have our function, which is the subject is equal to CL, the sine theta to the power L, and then I to the L, e to the IL phi. Sorry, the E and the L look very similar. The phi changes shape every equation, so I add a little bit of confusion for you. Hopefully this keeps you awake. Okay? Good. So, this is the solution. Now, obviously this is the solution for the wave function associated to this state, but we still have to get all of this. How do you do it? There is a standard procedure to do that. Our work is essentially solved. I mean, we do not have to solve any other differential equation. What we have to do is to apply L minus. Okay? You know that if I apply L minus to a function like this, what I get is the square root of L plus 1 minus M minus 1 times, I erase the factor, times L minus 1, okay? So I apply it to L, and I get L minus 1, but I have to keep track of this square root. And then I apply to L minus 1, and I get L minus 2. With the square root, obviously. Okay? So I do it, I mean, it's a machine, essentially, that can do it. So let me just do it in one example. In fact, there are two examples that you can easily work out. The first is L equals 0. L equals 0 is ultra trivial, right? This is just 1. This object here is a constant, sine theta to the power 0, which is 1. This is 1, so a constant. Okay? How much should be the constant in such a way that the normalization into the full solid angle is 1? The result is simple. Y 0, 0 of theta and phi is equal to 1 over square root of 4 pi. Okay? So if you take the square, you integrate over the solid angle, which is 4 pi, remember? And you get 1. This is called the S states in atomic physics. Okay? They are completely symmetric over theta and phi. Okay. When they say, take an electron in the hydrogen S orbital, that is the wave function of the S orbital. Okay? Nothing could be simpler. As far as the radial, the theta and phi variable is concerned, obviously there is a radial function, but this we'll discuss later on. Okay? Good. Let's do L equal 1. Now, I know Y 1, 1. Okay? That is equal to theta and phi is equal to C1 times the sine of theta times e to the I phi. Okay? Good. C1, you can calculate from the formula I just gave you before. It is equal to minus the square root of 3 over 8 pi. Okay? In such a way that if you integrate, really it becomes normalized to 1. Fantastic. Then let's apply the rule. Okay? So if I apply this rule to a state 1, 1, okay, I obtain 1, 0. What is the coefficient? Well, this is the square root of 1 times 2, so 2, minus, I put here n equal 1, so this goes away, so it's the square root of 2, okay? So this object is just square root of 2 times 1, 0. So if I want the 1, 0 state, so y 1, 0 of theta and phi, I have 1 over square root of 2, just the square root, times L minus applied to y 1, 1 of theta and phi. Is it clear? Now, question, what is L minus? I gave you here L plus, okay? Now I tell you L minus. L minus has a minus here, and you can show that there is a minus here, a plus here, and nothing else. Okay? So the remaining thing is the same. Okay, so you do it, you apply these two terms, okay, to this function here. By the way, the function is, let's write it explicitly, is C1, the sine theta to the power 1 times e to the I phi. Okay? So this term acts on the sine only and transforms it into a cosine. This terms also transforms the, remember that this object here is cos theta over sine theta. So also makes the sine disappear and transforms it into a cosine, but it also acts on this object, bringing down a factor I. Okay, if you put together these two things, you deduce very, very simple algebra, but please do it yourself, minus square root of 2, because you get the factor 2 partially cancelled by this square root of 2 in the denominator, C1 times the cosine of theta. No dependence on phi, because this object here gets cancelled by the object there, which is kind of obvious. I mean, if I have m equals 0, I know pretty much on general grounds that the dependence on phi has to be 0. I mean, it has to be 1. Is it clear? Is it clear? Yes. Oh, good. So this function is simply equal, just write it explicitly, square root of 3 over 4 pi times the cos theta. Okay? And then you can do the exercise once more. Apply. Yep.
The Lx minus I Ly, the cos theta over sin theta, is it plus or minus?
It's plus. Sorry. This is, I mean, faint, but plus. In any case, it's in the notes, don't worry. And you have to repeat it yourself to make sure that I do not include it in my notes just a misprint. Okay, so try to do it really, if you really want to have control. Then you do the same story, applying L minus to 1, 0. I don't do the algebra, you get another state. I write it here. 1 minus 1 theta and phi equal to square root of 3 over 8 pi sine theta again, and then I get e to the minus phi this time. Okay? Good. So here are the three states. One is this. Okay, then I have the 1, 0 state, which is this. And then I have the 1, -1 state, which is this. These are the three spherical harmonics for n equal 1. They are called the p states. Okay, again from atomic physics jargon. Now you often see plots of this states. In the plots they look like this. Well, first of all, these are angular spherical harmonics. You can define Cartesian combinations, which are the following thing. Suppose that I take let me just get some space. Suppose that I take 1 over square root of 2, y1 minus 1, so the last one we determined, minus y1, 1. Okay? If you do it with the minus sign, you realize that I get e to the minus minus e to the plus here, and what you get is the cos phi. So you get square root of 3 over 4 pi, then I have the sine theta, and then I get the cos phi. Okay? Because there is also a minus sign, extra minus sign here. Okay? So if you take the difference between this and this, you actually get the sum of the two exponential with opposite sign. Then you get the cosine. If you determine I over square root of 2 times y1 minus 1 plus y1 plus 1, guess what you get? Same object, square root of 3 over 4 pi, sine theta, I guess, sine phi. And the third one is absolutely identical, you don't touch it, so it's square root of 3 over 4 pi cos theta. Now look at these expressions, okay? Cos theta, sine theta cos phi, sine theta sine phi. Does this remind you of anything? Remember the rules for x over r, y over r, z over r are. This is cos theta, this is sine theta cos phi, and this is sine theta sine phi. Okay? Yeah. This is the reason why this orbital is called the pz orbital. This orbital is called the px orbital. And this orbital is called the py orbital. Okay? If you actually try to plot them, you will see that they are in fact those funny objects that you see in books. Okay? Precisely aligned along the Cartesian axis. So for instance, if this is z, x, y, the pz is something like this. Okay? Now, I don't draw three-dimensional things, but imagine two round symmetrically, with respect to, remember, phi is this, so the function doesn't depend on phi. That's the reason why it is totally symmetrical. Now, you might ask, why it has this funny shape? What I really draw here is if you take an angle theta, I draw a point proportional to the function, okay? So this object here is simply a line which is proportional to the cos theta, okay? So here is maximum, 1, and then it goes down, okay, up to 0. Now obviously, in this region there is a plus, because the cosine of theta for theta from 0 to pi over 2 is positive, and here there is a minus. So in some sense, there is also a minus and plus sign if you really want the wave function. If you want the modulo square, so the charge distribution in some sense, then it's irrelevant. The same thing happens for px, simply along the x, although it's more difficult to get it, and py. And this is important when you make chemical bonds, obviously, because the fact that an electron stays in a certain orbital, which has a given spatial directionality, makes a difference if there is another object here, another atom, with an electron, for instance, in a similar orbital, which can make a nice overlap of bonds and create a stabilization of the molecule, for instance, okay? So this is, I mean, as you know, an important fact in the crystal field effect, in the bonding of molecules and so on and so forth, okay? But this goes into real solid state physics somehow, okay? Good, is it clear? So important distinction between spherical harmonics and the Cartesian combinations. And I ask you as an exercise to repeat what we just did for L equal 2. So constructing the 5 D states, that's the way they are called, which look in this funny way. They are slightly more complicated than the one I drew, okay? But they are very important for discussing property of transition metals and so on and so forth. You often hear about dx squared minus y squared and so on and so forth. Try to make sense of them. Good. Okay, so hopefully this provides an illustration of some of the techniques of this theory of angular momentum applied to constructing explicit functions, okay, which are eigenfunction of L square and Lz. And as you realize, I had really to apply very little differential equations, except Lz, okay, very simple, and this L plus story. I mean, very, very little things. Certainly I didn't have to find the eigenfunctions of this object. Okay, now let's discuss spin. Okay. Which is the really new actor in this class. So far we have discussed about states, but having in mind always wave functions, okay? Now, okay, so the experiment that revealed the fact that there is spin in nature was conducted in 1923. So actually slightly before the quantum mechanical theory was formulated by Schrödinger, Heisenberg, and later on Dirac. And it was done by Stern and Gerlach, who performed the following experiment. You evaporate from some oven, some furnace, silver atoms. Okay, you take a little bit of silver, you just heat it up, and silver atoms are spitted away, they evaporate, okay, don't breathe too much there, but they come out of a little hole.
Professor, can you change later?
Yes, but I will get an equally bad. You have a personal reserve.
I don't know if they are good.
I see. Okay. So, atoms are spitted there, in this way, okay? And if this is large temperature, they are emitted with a large velocity. Remember the Maxwell distribution, right? So they have a very good velocity. Then you take a screen, you draw a hole in the screen, the velocities that are too inclined just missed, and you create a nice beam of rather fast silver atoms that pass the screen. And then you put a magnetic field here, okay? So you put two magnets, North Pole, South Pole, okay? In a way that is inhomogeneous, okay? So if I go, say, Z, this axis, okay? Now I draw the section of these two magnets in this way. This is the North Pole, and this is the South Pole. Okay? So as you see, this is a very shallow object. Okay? And here there is a very acute protrusion. Okay? Now, so this is Z. Okay. Why do they do that? Because they want an inhomogeneous field. So they don't want a homogeneous field. If you want a homogeneous field, you just make two flat things. And if you are away from the borders, the field is roughly homogeneous. They wanted a field that is in fact stronger here than here. Okay? So along this axis, which is, by the way, the axis over which the atoms fly and come into this little chamber. The field is more intense here than there. Okay? Because, as you know, in electromagnetism, sharp corners make more intense fields. Okay? Well, never mind. This is just life. Okay, field is more intense there. Good. Then they put a screen, okay, here, and these are silver atoms. If you think of them having some magnetic moment, they will interact with the magnetic field. You remember that the interaction potential, R is the position of the atom, okay? So it's the center of mass of this atom, is equal to the magnetic moment, scalar product, the magnetic field, okay? This is classical electromagnetism, okay? A moment, we try to align with the field, right? Now, if the field doesn't depend on R, true that the moment would like to align, but the potential is totally independent of the position, right? If the magnetic field is the same everywhere, the potential is totally flat with respect to the position, which means that the force is zero, okay? So if the magnetic field is constant, as you realize with arrangements like this, okay, then no force. So your experiment is dull. But they do an inhomogeneous magnetic field, which means that this object depends on the position, but particularly depends on the height from the corner there. Okay, so if I plot, for instance, so 0, zeta equals 0 is this corner here, and it's here, and I plotted B, the Z component of the magnetic field versus the distance from this corner. This is larger, and this is smaller, okay? So there is a derivative of BZ with respect to Z, okay? Which is in particular negative. Good? Okay. Now, suppose that I have a magnetic moment coming into the object. And suppose that the magnetic field is, say, the magnetic moment is aligned along plus Z, so with the field. All right? So the field is along Z, and mu is positive. Then I have plus, so say a moment which is up. Then the field, the potential is plus the value of this magnetic moment times Bz. What would you like to do if you were a magnetic moment up? Where would you go? This is a difficult question. You are a magnetic moment pointing upwards. You try to go towards the low field or the high field. You want to reduce your potential. Vacuums travel towards minimal the potential. I mean, Newton's equation. Nothing. You have a kinetic energy and you go towards the minimum of a certain potential. The minimum of the potential is where B is small, right? So you go here, okay? So around this object here. If you are a magnetic moment opposite to the field, your potential would be minus mu times Bz. Where would you like to go? Where the field is maximum to decrease the thing. So you would really go here. Okay? If you have a magnetic moment anywhere between these two regions, you select any intermediate situation. Okay? So classically, what would you expect? You expect to have a certain fan, a certain blob of every atom decides, depending on the direction of this magnetic moment, along Z, I will go here, 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 and you would expect some large blob of hitting atoms on the screen. What they find, strikingly, is the following situation. Two spots, sharply defined, okay? And not a big blob. Now, obviously, this means, so again, this is close to the North Pole. You see, this object went towards the North Pole, and then straight here, there is no magnetic field in this region here, so you are amplifying your deviation, and you end up here. Yeah, these other objects went through towards the South Pole, and then you go straight, and they went there, right? So who are these objects? These are, again, objects with the magnetic moment pointing down, and these are objects with the magnetic moment pointing up. All the other magnetic moments do not exist, evidently. Only two possibilities. A very strange result. Okay? Indeed, if you think classically, you know that magnetic moment for, these are electrons orbiting in some sense, right? On the silver. You know that for an orbiting particle, a magnetic moment is minus, for an electron, is minus the charge divided by twice the mass, the velocity of light, the angular momentum. This depends on the unit you use. This is a very, very, very sad story about electromagnetism. I'm sorry, I'm not responsible for that. This is not international units, this is CGS units. Otherwise, you would have no C there. Never mind. I mean, let me remind myself of this very tragic event in the life of a physicist. Okay, now, you realize that whatever is the orbital angular momentum of this thing, there's no escape. Orbital angular momentum, we just saw, either is zero, no effect, or it has three values. After all, I want the z component of that object, you see, because I am taking the scalar product with a field along the z direction. So what I really need is this. And Lz can have 3 values, 5 values, whatever. There is no way you can have only 2 values. So there is something that, even if I think quantum mechanically, I cannot make sense of these 2 spots. And the answer is obviously that in the general theory of angular momentum, we saw that the J are of 2 types. The integer ones, which we already encountered, one example is the L, the orbital angular momentum. But then there are the half integer ones, which evidently are appearing in this case. Because if I have, for instance, a value 1/2, okay, then I know that I can have two states. One with plus 1/2 and the other with minus 1/2, okay? So evidently these are the two objects appearing in this experiment. An angular momentum which is not of orbital origin, but is of some strange intrinsic origin. Electrons do possess this strange intrinsic angular momentum, which is called the spin. And for an electron, it has just two possibilities. So if you can be plus or minus, okay? And notice that there is an extra minus sign. So really, this is true also for the spin, okay? So the magnetic moment associated to a spin up is really pointing down. So this object here is really a spin up, hopefully. And this a spin down. No? I mean, just verify. I did my algebra with minus signs. I might have been wrong. Yeah. What? Now, what I got here is the magnetic moment, the mu z. Okay? But since there is a minus sign with respect to the spin, mu z pointing up means that the spin is down, actually. That's where. Okay? Good. So, in some sense, these people discover that electrons in silver do possess another strange angular momentum, which is not of orbital origin. Well, I mean, quantum mechanics, the theory that I explained to you yesterday was developed in 1926 by Born, Heisenberg, and Jordan. Okay, so the theory of angular momentum. So these people didn't know, obviously, any of these things that I'm telling you, but certainly the outcome is striking, and it took the genius of Dirac, okay, in 1930 to actually formulate a relativistic theory of quantum mechanics, which involves four-dimensional wave functions, which in the appropriate limit, which is the non-relativistic limit, really gives you the spin as an emergent quantity, okay? So the theory came much later, and how the spin emerges, okay, and other things like spin-orbit interactions and all this kind of things comes really from a certain limit of the relativistic Dirac equation, which I will certainly not do in this course. So I will ask you to take as a fact that if I write for you the Hamiltonian, say, of an electron by the way, these are silver atoms, but you could, if you want to think of them, you could think of hydrogen atoms. So you could think of a nucleus and a single electron orbiting around this nucleus. Why? Because silver atoms have a field shell, and then they have a single unpaired 5s electron. Okay? Very outer symmetrically s equals 0 electron. All the others nicely compensate their magnetic moment. So you can think of a single electron if you want. You could think of hydrogen. It would be the same, mentally the same object. You don't do experiment with hydrogen for a simple reason. Hydrogen don't like to stay alone before molecules. Okay, so if you evaporate things, you have H2 molecules coming out, not H. Okay, so you use silver. All right. So the Hamiltonian of this hydrogen atom, sorry, it is hydrogen and H Hamiltonian, same symbol, is the orbital Hamiltonian you would write for an electron in the hydrogen atom, so the p square over twice the mass. We'll see better this next time. Minus e squared divided by the distance from the nucleus. More about this later on. There is an Hamiltonian that governs the orbital motion, kinetic energy and potential. But there is an extra term, which you clearly see when you do the non-relativistic limit of the Dirac equation, which is written in the following way. This is in fact S divided by h bar, by the way. The mu b that is here is the so-called Bohr magneton. Bohr magneton. What it is? Okay, suppose that I ask you, given this expression for the magnetic moment in terms of the angular momentum, I ask you, what is a quantum of magnetic moment that you expect in nature? Well, quantum of Lz is h bar, okay? H bar, 2h bar, 3h bar, remember. The natural constant in front of an angular momentum is h bar. So obviously, if I put here h bar and I think of dimensionless object, this quantity here has the dimension of a magnetic moment. It is in fact the quantum of magnetic moment. It's called the Bohr magneton. Okay? Given E, h bar, the mass of the electron, the velocity of light, you calculate this magnetic moment, which is the elementary magneton. Now, this object here, again comes, in the Dirac theory would be 2. Okay? It's called the Lambda G factor. It has corrections in QED, but never mind. Don't ask, please. Okay. Nicely, the 2 with the 1 half that comes from the spin almost precisely cancel. Okay? So what you have is that, say, the spin up have an energy plus mu bb, okay? Plus mu bb for a spin which is up, this one, okay? Because there is a plus 1 half from there, and the spin down has an energy minus mu bb. This we will see later is called the Zeeman splitting of the two states. So, due to the fact that the Hamiltonian contains a term that couples the magnetic field with the spin, the two spins are no longer totally degenerate. They actually acquire one gains energy, the spin down, and the spin up loses energy if B is positive. Okay? So this is the spin down, and this is the spin up. Okay, this again, I will not derive for you. You have to take it as a word. Okay, shall we make a 2 minutes break so that I can search for a new piece of chalk? Okay, so let's take a break. What is this? Ah, fantastic. I had here beautiful chalks. Huh? What?
The recording is.
I will do a very drastic approach. Just throw away those things. I mean, they have to put reasonable chalks. Otherwise, it's a mess. Interrupt this. Okay? So we start again, and we consider the Hilbert space made by this two-dimensional object. So I have S equal to 1/2, M equal to plus 1/2. Okay, and the other is S equal to 1/2, M equal to minus 1/2. Two states, right? I don't call J this principal quantum number, I call it S. In the same spirit as I call L for the angular momentum. And this is still M, and M goes from minus 1/2 to 1/2. Two states. To make things slightly shorter in my notation, sometimes I might use different notation. For instance, I can use this as plus, and I put an index Z, means eigenstate of SZ. Okay, remember that these are eigenstates of S square and SZ. Okay, with eigenvalue plus or minus 1/2, and for S square with eigenvalue S plus 1. Okay, you remember this basic fact. So I call plus Z and minus Z, meaning plus 1, plus 1/2, minus 1/2, without this object. Sometimes I will also indicate by up or down. Okay, remember, up and down for the spin, not for the magnetic moment, which is precisely the opposite, unfortunately. Yep.
I want to ask, why do you? I know this is the spin of electron, which is half, but in this approach, why do you choose it as half? You said it's a half integer. It can be 1/2, 3/2, and so on.
Well, if it is 3/2, there are 4 spin states. And you don't see 4 spots.
Oh, so it depends on the spots.
Oh yeah. The experiment pins down the fact that the spin evidently has to be 1/2. Yes, 2. Okay? The smallest. I mean, it's very nice. If it was 137 divided by 2, it would be a horrible thing. No, it's 1/2. The nature is, really essential. Okay, good. So 2 states. These are 2 objects in a Hilbert space. So my Hilbert space is made of this and of that state. Obviously, also by any combination of them. Okay? So the Hilbert space for the spin is made by all spin states that you can form by just combining, for instance, with a complex number Z plus, the plus state, plus Z minus the minus state. Okay, is it clear? I have 2 objects, 2 basis states, and I can combine them with 2 coefficients. Okay, so if you want, I can associate in a unique way the matrix representing this object with a 2 component column vector, so an element of C2. Remember, given a basis, any n-dimensional Hilbert space can be identified with a column of n complex numbers. Right? And here it's 2-dimensional, the simplest, and therefore I have 2 numbers, the component of the up and the component of the down, and you can sum them. Okay? Linear combination of them. Is it clear? This is absolutely the simplest Hilbert space in the whole world. Okay? There's nothing simpler than this. You realize, with respect to wave functions, infinitely dimensional objects, 2-dimensional things, we work with 2x2 matrices as regarding the operators, 2 component vectors regarding the states, and so on and so forth. Okay? Good. Do you know how to, for instance, make sure that the state is normalized? How you do it? If I want a normalized state, I will take some time. These are simple things, but I know by experience meaning here is that they still come a bit difficult to digest, okay? So suppose that I ask you the size pin, and I pretend that this should be 1. What would you need to do to these two numbers? What condition would you need to impose? Okay? Remember that you can work, for instance, with column, z plus, z minus, and then I have to multiply by the corresponding bra, which is z plus star, z minus star. Okay? And you do this times this plus this times that. So z plus module square plus z minus module square. If you are not happy, which you might, try the direct way. So substitute this in here, and the corresponding bra, which is essentially z plus star plus z minus star minus, okay? And remember that these two states are orthogonal and normalized. So for instance, if you get plus and minus, this is 0, okay? And also 0. Okay, so you use the normalization of the basis and you immediately arrive to the fact that the norm is simply z plus square plus z minus square. Is it clear? So to specify a spin, I need essentially two complex number with one condition, okay, which is the normalization, which is a lot of information, by the way, okay, because I need essentially 3 real numbers. Just to notice a classical bit, okay, on which our digital computer work is 1 0. I mean, it's a binary digit. Okay, very, very little information. Here, in principle, a spin, I will have, say, the up, the down, but also any combination that I can form, okay, with complex coefficients in front, normalized. So a lot of information in a single spin. And that is one of the things that people who do quantum information would like to exploit, which is not there in our digital computer. Yeah?
Why do you say three real numbers?
Well, because 2 real numbers for a complex, 2 for a Bias-Hartrott, so 4 real numbers, but I have a condition that this is equal to 1, okay, so 1 less. Is it clear?
Oh.
2 real number for this, 2 real number for this, 4. Minus 1 because I don't care for the modulus. I mean, it's
by condition,
the condition. Yeah. If I ask you what is the dimensionality of this space, you count the dimensionality in this way. In other words, it's not R2 and R2, but it's a sphere in this 4-dimensional real space because I fixed. Is it clear?
Okay.
I mean, this is something that I'm not a mathematician, but I just count with my fingers, and up to 4 I can do it. Okay.
Is it like when you're solving the like a group matrix like SO3 or something?
Yes, but that is too it is related, obviously. But I mean, think of if I ask you the set of points such that x squared plus y squared is equal to 1. Okay, these are the points in the plane, so R2. Okay? Here I put a constraint, and this is just a circle. So I'm one-dimensional, I need just one angle, in some sense, to specify this thing. Okay, so from 2 dimension to a one-dimensional circle. 1. Okay, and in the same spirit, rather than 4, I just get one constraint, and I get 3 real numbers. But still a lot of information encoded in the spin. We will study in a while spin in different directions. Okay, we'll see how to work with it. Before insisting more on the spin, let me present to you something which is a bit formal, but useful and important. It is It is called the tensor product of Hilbert spaces. So this is something not completely trivial to digest, so please take a moment to concentrate. Suppose that I have some Hilbert space, which I call HA, with some basis that I have selected, which I call phi A M. Okay? These labels M just go over the states of this Hilbert space of, say, system A. And then I have system B, okay, which is similarly has a Hilbert space with a basis, which I call phi B of N. Okay? Now, in a while we will understand what can A and B. A and B could be two different particles, or the orbital degrees of freedom of a single particle and the spin degrees of freedom of the same particle, or even simpler things. I will give you one example in a second. Okay, so suppose that I have a particle in 2 dimensions. A could be the x part of the coordinate, and y could be the y part of the coordinate. Okay, these are two Hilbert spaces associated to function of x and function of y. I want to glue them together to make what is called the tensor product. Okay, so the tensor product is defined in the following way. First of all, it has a funny symbol. It is called like this, okay? It is a Hilbert space with a basis of pairs, okay? You take one element of this and you pair it with another element of that, so you can do it in a product number of ways. Okay, here they are. This is one element of this times one element of that. Okay? Never mind for the symbol, just keep it. Okay? It's a pair, which you write it like this. Obviously, with all for all m and for all n. Okay? Good. What do you do with those pairs? This is a basis. Okay? This is a basis for the tensor product. So I can write a state belonging to this Hilbert space. How? Well, I can linear combine this object. So I can sum over m, some coefficients, which I call psi m n, and then I have the element of the basis, phi a, m, phi b, n. Is it clear? Just use it as a rule, okay? The element of the basis are this funny symbol in between a pair of states, one of A and one of B, and then I just superimpose with coefficients, complex coefficients. Okay, this is the rule for getting the states of this product Hilbert space. Example, and in fact, I will give you the most simple example that you can think of. Suppose that this object, okay, is actually the Hilbert space associated to, say, the coordinate x. Okay, so it's generated by functions of x. Okay, could be, I don't know, Hermite polynomials times Gaussian, whatever. Okay, and then I have B, which is the Hilbert space of the y coordinates. So other functions, in principle, they could be different. Don't think that this necessarily have to be the same functions. This might be plane waves, and this Hermite polynomials. It doesn't matter. I don't want to make the notation too complicated. I would need, in principle, to say that this are the wave function in the x direction, but it's clear from the index. Okay, so let's get rid of the extra thing. Okay? Is it clear? I take those two elements. What are the elements of this basis? They are simply phi n of x times phi n of y. Okay? What is this object here? It's a function of x and y, which I write as sum of m and n psi m and n, then I have phi m of x, phi m of y. Okay? Now, let me ask you something. The element of the basis are evidently factorized in the two directions. But is any function like this factorized as well? You realize what I mean by factorized function, right? A function of x and y is factorized if it is a product of a function of x times a function of y. Do you think that this object is factorized? The single object is factorized.
Yes.
But what about this object? Is it factorized or not?
No.
No. Do you know one condition, for instance, over which, with a non-trivial psi, this object is factorized?
It's equal to
It's m equal to n.
What?
the sum
M equal to n.
M equal?
To n.
No.
if everything
Dirac is what? Is a condition? Huh? Kronecker. No. It's not difficult, but if you have never seen it, it takes a while. So I'll give it to you. Take this function to be, so psi of m and n, this is a matrix. Take it as a product of two vectors, fn times gn. Okay, not all matrices can be written in this way, right? This is a particular matrix whose variation in m and n is factorized in this way. Okay? Is it clear?
But how exactly?
Huh?
How exactly?
How you want. I mean, suppose that I have a 2 by 2 matrix. Okay? Try to write a 2 by 2 matrix in this form. Okay? You will see that this is a matrix. I can write a 1, 1 element. So the 1, 1 element is F1, G1. The 1, 2 element is F1, G2. The 2, 1 element is F2, G1. The 2, 2 element is F2, G2. Now you see that for a matrix of this form, for instance, if I take the ratio of this with that, okay, F1 cancel, and is exactly equal to the ratio of this with that, because F2 cancel. While for a general matrix, here I would have psi 1, 1, psi 1, 2, psi 2, 1, and psi 2, 2. And it's not true that if I take the ratio of this with that is equal to the ratio of this with that. Okay, try. Try with some matrix. Okay? So matrices of this form are very particular. They have a name, by the way. But I forgot the name. Never mind. In any case, they are factorized. You see, the indices dependence is factorized into a vector which takes care of the dependence of n, and a vector that takes care of the dependence of n. Is it clear? What happens if you substitute this there? You can disentangle the sum over m and the sum over n. What you have is, in the end, that the sum over m gets the fm and then the phi m of x, and then you multiply by the sum over n, which takes the gn and multiplies by the phi n of y. And now you see that the miracle has occurred. This is a function of x expanded in the basis for the x state, and this is a function of y expanded in the basis of, this could be a Fourier basis or Hermite polynomial. Never mind for the basis, but you see that if this coefficient here is a matrix which is factorized in this form, then the resulting function is in fact a product function of the x and the y. But the general function, which comes out of the tensor product of these two x and y space, is not factorized. Okay? This is a very important thing to keep in mind. Okay? Only under special circumstances, the states of the product Hilbert space are factorized as a state of A times a state of B. Okay? So to return to my general thing. And this also applies if this is the orbital Hilbert space, so the space of the wave function, and this is the spin Hilbert space, which is what we just described. If I glue together those two Hilbert spaces by making a tensor product of them, the resulting states are spin orbital states, okay? But generally speaking, they are not factorized, mind you, okay? So don't think that any state of a particle with spin is made of a orbital wave functions times a spin state. That's not true. It is in general a combination of orbital times spin, okay? So, okay? So, how tired are you? Okay. So let me return to, after this exemplification, to the thing that I have in mind. So let's try to write now the state of a particle with spin. So A would be the basis of, say, Hermite polynomials. Just to give you an idea, this was an harmonic oscillator, for instance, or the hydrogen atom wave functions, whatever, okay? And B is the spin, okay? So these objects are simply two-dimensional objects. So these are simply, I will denote them by sigma, okay? Sigma could be is equal to twice m, okay? So it's equal to plus or minus 1, okay? Just to make the notation a bit more compact, okay? So what I would write here is that this is equal to the sum over m and the sum over sigma equal to plus or minus 1 of psi m sigma. Then I have the function phi m, the orbital part of the state, times the spin part of the state. Okay, so this is orbit and this is spin. Okay, and again, unless you take this object factorized, the resulting object is not factorized in orbital and spin. Okay? Now, in the notes you find many details of this, but I don't want to annoy you too much. Simply remember that, for instance, if I try to calculate the wave function of this thing, in principle I have to evaluate at some position x and with some spin sigma. What is this? This is the bra corresponding to a factorized state of this kind. Okay? So if I take a position eigenstate, tensor product, the spin along, say, up or down, this is a product state, which is my basis to express, for instance, the wave function. So I try to express the state in this basis. If you do it, generally speaking, you find some function of x, which however could be different from up and down. Okay? So psi up of x and psi down, yep.
The sigma equal to 2n, right?
Yeah, it's simply a short way of denoting plus or minus 1. M, remind you, is plus or minus 1 half.
Yeah, it is the same n.
What?
Other n.
Oh, disaster. Sorry. Erase. M here has nothing to do with the M here, that by the way is in the different position, is in order. These are simply M and M to consecutive integers.
Confusing in this.
Absolutely confusing. think of two labels, but not now, okay? So simply remember that when I write, so forget about this quotation mark M, okay? Which is the same M that appears here. This is the angular momentum eigenvalue. Now, M and N here, these are labels, okay? Which I in fact might call K and L. No, L is also impossible. Unfortunately, when you start writing, then the notation is a nightmare, because certain symbols you certainly cannot use, okay? H, never use H, I mean, because Planck has the copyright on it. And other things like this, okay, so it's a nightmare, nevertheless. Okay, so this is one good reason to introduce sigma, which is twice the M, which is plus and minus 1. So that I get rid of, so all this M that you find there, in fact, let me call it N, are just other quantum numbers, the orbital parts. Okay? In the notes you will find the detailed derivation. Okay? You will see that in principle, if I write a state in space and spin, it is a spin orbital function, psi sigma of x. And in principle, it is not true that this is only a peculiar factorized case when this object is made of a product of orbital wave functions times the z plus and minus that I was. So some complex number times a single wave function. You see the difference between this and this, okay? So here the up wave function and the down wave function are very different one from the other in principle. While here they just differ by a complex number in front, okay? So this is just factorized case. Very special, okay? The general case is this. Now,
Professor,
yep.
why do you underline here?
Where? Oh, sometimes I denote the vectors underline, sometimes with the arrow. Be merciful with me.
Oh, okay.
Okay. In the notes you will find boldface. Okay. So to denote that this is a position in three-dimensional space. Sometimes I put the bar below. Mathematicians tend to put the bars below rather than the vectors above. Okay. I mean, this concept of tensor space takes a while to digest, I admit, but try to carefully think of all the considerations that I do in the notes and try to digest it better. Okay? So in some sense, if I want a general state and I ask you write a wave function for the states, then you would write, in fact, a two-component wave function, psi plus and psi minus of x. Okay? Pretty much as if I tell you write a spin state, you write a two-component complex vector, z plus and z minus. Now, if I have the space, I have to have a two-component function, complex function. Okay? And by the way, Dirac worked with four components objects. Okay? So his fully relativistic theory requires that you work with four component things. Yeah?
What is the sigma? It's just the factor.
Which one? Oh, it's the same z that you have there. Okay, so this is just z plus and z minus that you have there. Complex numbers. Okay. So as you see, this is a very special choice. This is the most generic choice. If the functions are equal to this, then this becomes psi of x times z plus and z minus. Okay? Which is essentially a product of an orbital wave function times a spin, two-component spin. Is it clear? I don't know if it is clear, but just insist, okay? Try to digest, look carefully, because this is the only thing that makes things a bit more confusing. Now, remember that so far, we work with the Hamiltonian. For instance, I said that the orbital Hamiltonian, okay? P squared over 2m. What is this? How does it act? This is an operator. Where does it act? Obviously, it does act on the orbital Hilbert space only, okay? So this object works in the orbital Hilbert space. It works on the functions, okay? What does it do to the spin? What does it do to the spin? Nothing, okay? So properly, you would write it as identity in spin space times the orbital Hamiltonian acting on the orbital part of the Hilbert space. I wrote, and I raised, the fact that the Hamiltonian has the factor 2 UB, the spin, or B dotted into the spin, okay? Where is the orbital part here?
No.
Nothing, okay? This acts only on the spin. So I really should write this as plus 2 UB, identity in the orbital space, times this object acting on the spin, okay? Every time, if I have an operator, I know if it acts only on the orbit, only on the spin, sometimes on both. We will encounter in doing spin orbit later on an operator of this kind. Okay? L dot S. Orbital angular momentum times spin. This takes care of the orbit. This takes care of the spin. They don't look at each other. Okay? It's like two, this separation here is like a wall. Okay? An operator has an orbital piece, a spin nose, and the tail works on the orbit and the spin on, okay? So they don't talk to each other. Yeah?
Do you need to divide that by h bar?
H bar is always included here, and I tacitly, implicitly assume that this has been normalized and divided by h bar. But you are right. Okay, this is not the physical spin, but the spin divided by h bar. Okay, later on we will work with these things and you will get a bit more used to this thing, but please start getting some experience. All right.
Also,
I think I should stop. Yeah.
So in practice,
Yeah.
we usually do this tensor product calculation using matrix representation, or
Yeah. Very often.
is it using like this graph characterization?
We will do it. Later on I will show you how to do a little bit of practice with this, okay? You can decide to use this cat notation or the matrix representation. Depending on the case, sometimes it's more direct one, sometimes it's better to use the other. The important thing is that you have clear in mind what is the structure of the object. I did not define one last thing, okay? I told you, you take a space A, a space B, you take the pairs, these are the elements of the basis. I can form any linear combination. Exercise. Let's calculate the scalar product of two states in this space, okay? So, this I should have told you before. So suppose that I take the state psi and the state phi, and I calculate. Do not confuse this phi with the elements of the basis, okay? This is a generic state. I could use psi 1 and psi 2, but these labels in the, these indices then are a bit in conflict with this extra labels there, so it's the tragic story of notation. So there's no perfect notation. This is the only guarantee. So this is equal to, there is a sum over m and n coming from the, this object here, which involves what? It involves a phi, m and n, okay? And then I have what? I have the phi a, never mind, m times the phi b n, okay? This is the element of the basis, this is the vector. Would you like a new symbol here, if you want, rather than, what Greek letter do you like most? Other than psi?
Zeta.
Huh? See,
Zeta.
like this? Ha.
Yeah, that's
That's a good one. Okay, the state chi and state psi. One has elements, chi and n, times the element of the basis. Then I have the bra. So I have a sum over n prime. Use different symbols, please, in the labels. And then I have psi star, n prime. And then I have these two objects in the bra, okay? So I have phi a of n prime and phi b of n prime, okay? This is the same element, but just made in the bra. And notice that I wrote in such a way that this looks at his partner in A, and this looks at his friend in B. Okay? So it's a little bit farther away in the board, but for him, it's just close friend. Okay? So A with A, B with B. And then you realize that this is an orthonormal basis, so M prime. This is also an orthonormal basis, so there is a Kronecker M prime M, and the result is that obviously there is a single sum over M and N, and then I have psi star, M n, chi, M n. Okay? So the scalar product of two elements is calculated in this way. Is it clear? Okay. So please read this page and a half of the notes carefully to get some proficiency with tensor product. Okay? Good. I think we can stop.